Hello, welcome back to another video. So at this point you should be familiar with the volume interpretation of the determinant. What the volume interpretation says is that the determinant gives you the area of the parallelogram defined by two column vectors in 2D, and the determinant gives you the volume of the parallel pipette defined by three column vectors in 3D, and so on and so forth, higher dimensions. You also should have seen the following three properties of the determinant. The determinant of the identity matrix is 1. The determinant is linear in each column. Here, the notation V1 through Vn simply denotes column 1 through column n, and with each V denoting one column. The homogeneity of the determinant says that if you scale one column, say column j, with j between 1 and n, if you scale column j by a factor of c, then you scale the entire determinant by the same factor c. The additivity of the determinant says that if you add another column vector, w, to column j, then what you get is the original determinant plus a new determinant with column j replaced by w. The third property says that the determinant reverses sign whenever two columns are swapped. So here you can see when we swap column k with column j, you reverse the sign of the determinant, you get a -1 in front. As it turns out, these three properties are all you need to uniquely define the determinant. What that means is that there exists exactly one function that takes a square matrix with real entries to a real number while satisfying these three properties, and that function is the determinant. So in this video, I will show you how these three abstract properties are in fact consistent with the volume interpretation of the determinant. The first property should be fairly obvious, as the columns of the identity matrix define a unit square with area 1 in 2D and a unit cube with volume 1 in 3D. So we'll jump right into homogeneity of the determinant. Homogeneity of the determinant says that if you scale any column by a factor of c, you scale the entire determinant by a factor of c. So here in 2D, we have V1 and V2, the two column vectors, and the area of the parallelogram defined by the two column vectors, which is this one, is given by the determinant with V1 and V2 as columns. So if I were to scale V1 by a factor of 2, which you can see I've done here, you get this new parallelogram. And the area of this new parallelogram is given by the determinant 2v1 and v2. The homogeneity of the determinant says that this is equal to 2 times the determinant, 2 times the original determinant. So what it's saying is that when you scale v1 by a factor of 2, you scale the area of this parallelogram by a factor of 2, which is true. As you can see here, by scaling v1 by a factor of 2, you added another parallelogram which has the same area as the last one. So the area of this new parallelogram is double the area of the original one. So the homogeneity of the determinant makes sense. Next is the additivity of the determinant. So here, once again, you have v1 and v2, and the area of this parallelogram is once again given by determinant v1, v2. Now, if you were to add another vector, w, to v1, and you get the following resultant vector, v1 plus w, the area of this new, larger parallelogram is given by determinant of v1 plus w and v2. So this will give you the area of this new larger parallelogram defined by vector v1 plus w and v2. The additivity of the determinant will suggest that this is equal to the determinant v1, v2, which is the original determinant, which is the area of this parallelogram, plus determinant of w, v2, which is the area of this new parallelogram defined by w and v2. So what this is saying is that the area of this large parallelogram is equal to the area of the original parallelogram plus the area of this new parallelogram. So on the picture, you can see that this region overlaps. So all you need to do to show that this is true is to show that this triangle defined by v1, w, and v plus w has the same area as this triangle above. And this is true because these two triangles are simply translated versions of each other, with v2 being the translation vector. So you can see this point goes here, this point goes here, this point goes here. So the entire triangle is translated by v2. Therefore, these two triangles are congruent and they have the same area. So we have shown that the additivity property of the determinant makes sense. The third property, the alternating property, says that the determinant reverses sign whenever two columns are swapped. So when you swap column V with column J, you got -1 in front because the sign reverses. So far we have been talking about determinant as areas, as scaling factors. So what does it mean for area to be negative? So first, we have this matrix. This is not an example of swapping column, but this example is simply to show what it means for area to be negative. So here you have this transformation with a determinant of -1. So that tells you that the determinant doesn't scale anything. The transformation doesn't scale anything. So here you can see that originally you have this image K here. This is just for reference. And then after the transformation, the K has been reflected across the y-axis. So you can see that this matrix represents the transformation of reflection across the y-axis. And it has a determinant of -1. So a negative determinant formally means that the orientation of space has been reversed. What that means intuitively is that there has been some kind of reflection during the transformation, or that the page or the plane has been flipped over during the transformation. I will show you how that works. So the -1 determinant suggests that I can get from here to here simply by flipping over the page. So I will show you. If you flip the page this way, and you can see the original picture here, you can see that the original picture now becomes the transformed version. So you can see that the negative determinant means that the plane has been flipped over during the transformation. That's what the negative means. So here, let's look at what happens when we swap the columns of the identity matrix. So here, the determinant of the identity matrix is 1, so when you swap its columns, you're going to get -1 as the determinant. So here, you have the image before the transformation. Once again, you have K here for reference. So the transformation swaps E1 with E2, so E1 would go here and E2 would go here. And then you get the picture after the transformation. You can see here there's also the K has been reflected across the 45-degree line. So there has been some reflection during the transformation, as one would expect with the negative determinant. And I will show you that this in fact can be done by flipping the page over. So if you simply flip the page over this way, you can see that the original picture now becomes a transformed picture with K being reflected across the 45-degree line. So you can see here, whenever you have a negative determinant, it means that the page has been flipped over, or there has been some kind of reflection. So the third property says that you reverse the orientation of space, or you flip, or intuitively you flip over the page when you swap the columns of the when you swap two columns of the matrix. This can also be generalized to 3D when you have more than two column vectors in the matrix, but whenever you swap two columns out of many columns, then you get some kind of reflection. Or another way to think about it is that you kind of flip the plane over, and that's why the sign reverses when you swap two columns. So that's the third property. And before wrapping up this video, I have two final remarks. So, in some books you will see that the determinant is stated in terms of rows instead of columns. But those two are completely the same, because the determinant is invariant under the transpose operation. Well, this means that the determinant of A transpose equals to the determinant of A. And since columns of A are simply rows of A transpose, and columns of A transpose are simply rows of A, the statement that the determinant is linear each column is the same as the statement that the determinant is linear in each row. Second remark, suppose A is an n by n matrix, the determinant of A equal to 0 if and only if A has linearly dependent columns. The if and only if here means that if the determinant of A is 0, then A has linearly dependent columns, or if A has linearly dependent columns, then the determinant of A equal to 0. This is another property of the determinant which can be proven from the previous three. This is an incredibly useful property, because if you combine this with the invertible matrix theorem, you get that A is invertible if and only if the determinant of A is non-zero. That's it for this video. Thank you.